Okay, this is chapter 7.2, page 2 of the notes. Hopefully you've had a little bit of time to digest what was on page 1, and this is making a little bit of sense. So let's zoom in on the top here. Suppose we want to find the sine of A in triangle ABC. Sine is the opposite over the hypotenuse. And so if we are looking at angle A, again, that side opposite is the one basically you can draw a straight line to. So 3, the hypotenuse is the side opposite the right angle, so our 5. And so we get that ratio of 3 over 5, and that is the sine of angle A. And you guys, I am looking for a way to make this pen like not so fat so I can get a little more in there. I haven't figured that out yet, so I'm working on it. Okay, so example 2, we got triangle DEF. Notice here, like I said on page 1, if it's an ABC triangle, C is typically the right angle. Here we don't even have a C, but the sides are labeled. We know what we're looking for. So we want the sine of F. Here is our angle F. So the sine is, and I'm just going to put a note right here, opposite over hypotenuse. So the side opposite F, for F, this is the opposite side. This is the hypotenuse. I might as well label them all, which makes this the adjacent. So opposite is 12, hypotenuse is 13, and that's it. Okay. Cosine is adjacent over hypotenuse. The adjacent side is 5. Hypotenuse is still 13. If you can reduce them, reduce them. Can't really reduce these ones, so we're okay. Tangent, opposite over adjacent. So we have 12 over 5. And that's it. So the other 3 functions, if you go back to the notes on page 1, are just the reciprocals of the basic tangent functions. So cosecant is the reciprocal of sine, so hypotenuse over opposite. And I'm just going to flip this, 13 over 12. Okay. Secant is the reciprocal of cosine, so I get hypotenuse over adjacent, 13 over 5. And cotangent is the reciprocal of tangent. I forgot to list this as tangent. Tangent is opposite over adjacent. Cotangent is adjacent over opposite. So 5 over 12. All right. Triangle 2, we've got triangle GHI. I is our right angle. Notice here we have the 2 legs labeled, but we don't have the length of the hypotenuse. So when you have a right triangle, for any right triangle, I'm going to stick this over here. For any right triangle, we can use the Pythagorean theorem. So the Pythagorean theorem applies. Which says that the sum of the square of the 2 sides equals the square of the hypotenuse. Basically, we're going to take the length of the sides and square those. And we can use that to solve for C. So 8 squared is 64, 15 squared is 225. We add those together and we get 289. Is our C squared. I'm going to stick this in a different color really quick. To undo the square, we square root. and we get 17 equals C, which means the length of my hypotenuse is 17. And so now we can crank through those trig ratios fairly quickly. The sine of G is opposite over hypotenuse. Take a minute to figure out which side is opposite angle G. Kind of like one you can draw a straight line from. And we get the 15 is our opposite. So we have 15 over 17. Cosine is adjacent over hypotenuse. 8 over 17. Tangent is opposite over adjacent. So we get 15 over 8. Typically when I set these up, I will set the reciprocal function next to the original trig function. I kind of remember that one starts with S, one starts with C. So the reciprocal for sine is the cosecant. You're going to need to come up with a way to remember which are our reciprocal functions. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Fairly straightforward. It is a matter of figuring out what you've got going on in the triangle, okay? So let's take a look at this last one. We are given specifics, but we don't actually have a triangle. So what I'm going to do, because I am fairly visual when it comes to stuff like this, is I'm going to go ahead and draw a triangle in. Here's my right angle, C. The hypotenuse opposite is my 7. It doesn't really matter which I label A and B. I think I want to do that the other way. But I know the side opposite B is my little b, so this side has to be 6. This looks a little different than the other time we use the Pythagorean theorem. Okay, so here is my side A. If I take a look at plugging in what I have to the Pythagorean theorem, I don't know A. I do know B. And I do know C. So as long as we have 2 sides, we can find the third side. This one doesn't come out as neat as the last one. When we square root both sides, we get that A is the square root of 13. And so here's the thing. We are going to leave it that way, square root of 13. That is an exact number. We don't use radicals to count. But the square root of 13 is going to be between square root of 9 and square root of 16, so between 3 and 4 somewhere. If I crank it into the calculator and I get a decimal, it then becomes an approximation. I don't want that, okay? But here's the length of that side, square root of 13. So the sine of B, and notice here we're looking at different sides at this point. And I'm going to go ahead and see if I can color code a little better so that if you are just making sense of these, it's a little easier to follow. So there's my 6, there's my 7, there's my square root of 13. So the sine of B